Right, so in this video I'm going to show you how to find the centre of mass of a two-dimensional shape in a slightly easier way using vectors. So this is, I'm told here it's a uniform lamina. Lamina just means it's completely flat and doesn't have any kind of height, like a piece of paper, but even thinner. And it's uniform, which means that its mass is evenly distributed throughout, and what that means is we don't actually need to know what the mass is to be able to find its centre of mass, because we can say if it's uniform then the mass of each kind of section is proportional to its area. So what we can do is split up this shape into some different rectangles, of which it's easy to find the centre of mass of a rectangle because you just know it's in the middle. So if we split it up, let's say like this, into 3 rectangles, let's label them A, B and C, then all we need to do is find the centre of mass of each of these, and we can use our normal our formula that we were using before. Okay, so the formula that we used before is we said that x bar equals the sum, so the distance of the centre of mass from the origin, this was just when we had one dimension, was the sum of xi, mi, I'll put this in a different order but it doesn't matter, divided by the total mass, okay? So if that's what it is for x, it's the same. If we imagine this on a coordinate grid, where that's the origin, this is our x-axis, and this is our y-axis, we would be able to find horizontally where's the centre of mass using this, and we can find vertically where's the centre of mass using exactly the same thing. So the vertical distance from the origin is going to be equal to the sum of each individual mass times its vertical distance from the origin divided by the total mass. Okay. Now you might wish to work these out separately, but I often find it easier to actually just work them out all in one go using vectors. So you can actually say that the location of the centre of mass as a vector, x bar, y bar, is equal to the total of each mass times by its position vector xi, yi, and then divide that by the total mass. Okay, and that's what we can do here. So if we think about C, where is, so let's put this over here. In fact, yeah, let's go alphabetical order. So A, the area of that is 5 by 2, so that's the total mass, we're going to say, of that object is going to be 10. And the position of that centre of mass is, well, it's going to be 2.5 that way from the origin, and it's going to be 1 across there, but that is a total of 6, so it's going to be this, it's going to be 5, okay, because it's gone up by this 4, and then 1 more to be in the middle there. So the middle there is 2.5 that way, 1 that way, but it's 5 up from the origin. So then for B, that is 2 by 1. Yeah, so that's just the mass of that is just 2, or the proportional mass is 2. And then the location of its centre of mass is going to be 0.5 this way, and 3 vertically. Then for C, the area of that one is 6, so that's going to be its proportional mass as well. And the location of the centre of mass is 1.5 and 1. So that's the top there, and then this whole thing is going to be divided by the total mass, which is just a 10 plus 2 plus 6, so 18. Okay, and then we just need to work that through. So we've got 2550 1, 6. Then we've got 9, 6. And we're going to be dividing all of those by 18. Might be kind of easier to understand that if you put brackets and then multiply by 1/18. Okay, so that's going to be 1/18. Adding that up is 26. And this is going to be 62, which is so leaving it in exact form would look like that, but changing it to decimals, we're going to get about 1.9 there, and then 2.4 there. So the centre of mass is going to be 1.9 meters this way, so about here-ish, sorry, and then 3.4 meters up. So it's going to be, the centre of mass will be about there, assuming that I drew this to scale, okay? And that is just the vector, so we could say that's the position vector of the centre of mass, that's all that is.